We are continuing our discussion of polynomials, which we started before, talking about their average rate of change. But we're going to go ahead and talk about actual polynomial functions today, review a ton of vocabulary that you mostly have seen before in Algebra 2 or in Algebra, but I know that means that you've had a whole summer at least since then, so we'll go back over it. First things first, the zeros of a polynomial function. This is a huge vocabulary word. It's something you've seen since Algebra 1. Potentially in Algebra 1, you called it one of your rocks words. Does anyone know what all four of those letters stand for? Do we remember this? No, that's a good R word for algebra, but no. This one is the one everybody forgets. This one is roots. What is this one? Zeros. What's this one? X-intercepts and solutions. Those all mean the same thing. So a polynomial function p of x, if p of a is equal to 0, then the number a, the x value you've plugged in when it's equal to 0, is called the zero or root of the polynomial. Those all four words mean the same thing, but when we talk about a graph, for the most part, we're going to be using the word 0, but it means where the y value is 0, which is the solution, which is the root, which is the x-intercept. But you're going to see the word zeros a whole lot more. Further, and this is really important, if a, so the number you've plugged in, is a real number, and if x equal to a is a 0 of p, so if it's not imaginary, and it is exactly a 0, then you automatically know that x minus a, in parentheses, is a linear factor of the polynomial. So in Algebra 2, you would have used this fact to quickly factor polynomials using synthetic division, all of that business to get down to maybe something you could factor by hand, or you'd have an irreducible factor. We're not doing that today, but just trying to connect that to things you've done before. Some other things you might have seen before is called multiplicity. Have y'all seen that word before? Yeah, multiplicity means repeated roots or repeated zeros. If a linear factor is repeated n times, meaning it has an exponent that's not 1, then corresponding zero of the polynomial has multiplicity n. So whatever that power is the multiplicity of the function. So typically we know that a graph of a function polynomial passes through the zeros on the graph through. We know this because at zeros it crosses the x-axis. However, when a zero has a multiplicity that is greater than 1, the graph will behave differently near the 0. So in this example here, we have the function y equal to negative 0.1, parentheses, 1 plus 4, close, x plus 1 to the third, x minus 3 squared, and it's graphed here. Things we know automatically from those linear factors, the parentheses, is that you're going to have a 0 at negative 4, you're going to have a 0 at negative 1, and you're going to have a 0 at 3. Do we understand why? If you take each of those individual parentheses, set them equal to 0, and solve, you just do the opposite sign to solve a one-step equation. Those would be your zeros. And in fact, that's exactly where I see the zeros on this graph. Go ahead and highlight those for yourself. We have 3 places where this graph crosses or touches the x-axis, so it has 3 zeros. They just have different multiplicity. The multiplicity of the 0 is the degree of its factor. We can include the multiplicity when we list the zeros. So this is how we will do this today. For the zeros, instead of just saying x equal to negative 4, x equal to negative 1, x equal to 3, like I wrote above the function, we would say x equal to negative 4, multiplicity 1 is implied. X equal to negative 1, mult 3, from multiplicity 3, it has a 3 power on that parentheses. And x equal to 3, multiplicity 2. Importantly, at x equal to 3, since that multiplicity is 2, the graph of the function is, we're going to highlight this word, tangent to the x-axis. Last year, you would have just used the word bounces off the x-axis. And this is exactly what it does, but that is called being tangent to the graph. Tangent means touches once and goes away. So if we look at this graph a little bit more closely, we see at negative 4, it crosses through. So I'm going to write the word through just to make it very obvious to myself later when I'm looking at my notes. At negative 1, it crosses through. Both of those zeros have an odd multiplicity, a multiplicity of 1 or a multiplicity of 3. But at x equal to 3, we have a bounce. It is tangent to the x-axis right there because it is an even multiplicity. So any odd multiplicity will pass through, any even multiplicity will bounce. It will be tangent to the graph. So for each of the following polynomials, without graphing it, we're going to determine the degree of the polynomial, find all of the zeros, and then state the multiplicity for each zero. Now here's the deal. Before today, when I asked you degree, usually you just looked at the leading coefficient, you saw the power, and you're like, 3. 3 is not the answer here. How come? Good idea. So when normally you look at these, you just look at like this one, right? The largest power. That is technically the largest power showing. But is this in standard form? No, it's in factored form. So if we were to put it in standard form, we're not going to because that's way a lot of work. If we were going to put it in standard form, how many x's would I eventually multiply together? There's 3 here, there's 1 here, and there's 2 there. How many total is that? 6. This is a degree 6 polynomial. I basically take all of the powers of x's that is possible and I add them together. We have a cubic, we have a single linear factor, and we have a squared factor, so that totals up to 6. If I were to find the zeros, it's already in factored form, which is really nice. I'm going to clean mine up so we can actually see it. The zeros, I don't even have to really do much work because I know the first factor, if I set it equal to 0, x is going to be equal to 0 with a multiplicity of 3. Again, that's this part right here. If I set this little chunk equal to 0 and solve for x, anything multiplied by 0 is 0. So x equal to 0 with a multiplicity of 3. What's the second 0? What's that middle parentheses going to give me as a 0? -1. It's usually implied that if you don't talk about multiplicity, you're talking about multiplicity 1, but for the sake of our notes, we're going to just write it down. What's the third 0 here? +4. What's its multiplicity? 2. So for this one, which of the zeros would be tangent, or which of the zeros would bounce? 4. Why 4 only? The multiplicity is even. Yes, the multiplicity is even. Okay, let's try it again. And by let's, I mean you. You have part B. See if you can tell me the degree and then the zeros with their multiplicity. And it does have a little trick in it, so I hope you don't fall for my trick. Okay, we should have at least gotten this far. What's the degree? Say it with confidence. 6. We know 6 because we have a squared term here and a to the 4th power there. Add those together. This is going to be degree 6. Okay, here are the zeros. I want to see if you know why I got the zeros that I did. Yeah, I see your faces. Why is that the right answer? They definitely have to add up to 6. 1 + 5 is 6, so I'm good there. But where did the -2 and the 2, where did all of this come from? Great question, Miss Quigley. Here's what I did. If I take this term, and I did this in my head, and I solve for x, when you take the square root, what do you have to remember to put in front of it? Plus or minus. So this is plus or minus 2. So then the second one, when I set this guy equal to 0, just the term itself, we get x equal to 2. The blue part has a multiplicity of 4, and the red part, each of those has multiplicity 1, but then I've used the number 2 twice. So I just say them all together. Is that okay? Do we follow? Now that's fine and dandy, and these have been super duper simple, but what happens when you get a problem like C? Are these already in factored form? So which means we have to factor them first before we find the zeros. We can tell the degree without factoring though. What's the degree of this function? The degree is 5. Why? Because I know I said add up all the powers, but I didn't add up all the powers. You'd get like a whole bunch of numbers. How come? It's only 5. Just the first ones. Because if we break this apart and factor it, we're going to see that there are 5 linear terms. Okay. Okay, so let's factor. I'm actually going to move this down a second so that I can factor it next to it. You can leave yours there. If we start to factor this, what do you notice that whole first parentheses has in common? X. Okay, great. We're going to factor out X because we always take a GCF out first so that it's smaller, it's easier to manage. For the second one, we're going to go ahead and guess and check. To guess and check, we haven't done this since like the pre-chapter. We're going to set it up with the coefficient of X, which is 1 in the first parentheses, and a plain X in the second parentheses. We look for factors of 12 that will add to 7. What are some things, or negative 7? What are some things that multiply to make 12? 1 times 12, what else?
6.
3 and 4, 2 and 6. Okay, to speed us up, we're going to try 3 and 4. If I multiply these, I get 4 and I get 3x. Is there a way to make 7, negative 7, out of 4 and 3? Both negative. Okay, cool. Look, I've already factored that second one. Can you guys factor that trinomial that's in the center, please, using guess and check? I just want to make sure we got it. I know I went fast through that guess and check. But tell me what to put there after a second. X minus 3 and x plus 2. Very good. Okay. So if we go to look at all of these things, what do you notice about one of the linear factors we have in this entire expansion? Specifically the ones I'm pointing at right now. They're the same. So what's that going to mean when I list the zeros? It has a multiplicity of 2. So if I put back, we already talked about the degree. I erased it, but I'm going to put it back. We said it should be degree 5. The zeros here are going to be x equal to 0 with a multiplicity of how many? How many times is 0 going to be one of my solutions? Once, because x is not squared or anything. We would have x equal to, I'm just going to go in the order I see them, 3. What's the multiplicity of that one? 2. We have x equal to negative 2 with a multiplicity of, question mark, 1. And then if you can squeeze it in there, x equal to 4 with a multiplicity also of 1. So these problems can be really simple if the factors are already there for you, or they could require you to factor quickly. But we're going to get faster at factoring, so it's not going to be a roadblock for us. Now that's all fine and dandy, and I kind of read over the instructions here, but there's something really important in these instructions, specifically this part right here. What word has it added to the question instead of just saying find the zeros? The real ones, which means we're still responsible for understanding that not all zeros are real. Some of them are imaginary or complex. When you're talking about complex roots, you're talking about the non-real zeros. That's going to be another word you see, non-real or imaginary or complex. Complex roots means that you will straight up not see them on the graph. So in the example that you see right there, that is x squared plus 1. Does it cross the x-axis at all? Highlight your x-axis for me, please. Does it, that quadratic, does it ever cross the x or touch the x-axis? No, which means we can't just look at the graph and identify all of the zeros. We actually have to find the complex roots in another way. And I've actually done it here for you. To find the zeros of f of x, we would set x squared plus 1 equal to 0. You subtract 1 to the other side. You take the square root, including the plus and minus. But the square root of negative 1 is I. So it's a complex number. Here's something that's super important. All imaginary roots, like the one we just saw, come in pairs. If a plus bi is a root of f of x, then so is a minus bi. They're called conjugate pairs or complex conjugates. You'll see that word too. So this is not going to trip us up either. If you see that there is an imaginary or complex number that is a root or a zero of your function, you automatically know that there is another one. So for example, if I give you the piece of information that 4i is a zero of your polynomial, you automatically know what other imaginary number is also a zero. Negative 4i. You change the sign of the imaginary part. That's what happened when I went a plus bi and a minus bi. So if, for part B, if negative I is a 0, what also is a 0? Positive I. if 2 minus 3i is a 0, what else is also a 0? 2 plus 3i. If negative 4 plus 2i is a 0, what is also a 0? If you ever get a complex number as a root or a 0, it has to have its other pair included. So far, has this stuff felt familiar to things we've at least heard before? Maybe you don't remember it all, but you've heard these words. Great. That's why I'm going kind of fast today, because you've seen this before, just maybe not in this exact way. One of the other things you would have studied in Algebra 2 is called the fundamental theorem of algebra. It's so fundamental. You're also like, I'm taking Algebra 2, and I've been doing algebra since like 7th grade. Why am I just now learning about something called the fundamental theorem of algebra? It's just the way it's named, okay? Basically, it says that a polynomial of degree n, so we're talking about the degree, again, of the polynomial, has exactly n complex zeros when counting multiplicities, meaning the total number of zeros in the polynomial will be the degree, not necessarily the number of real ones, the total number of real and non-real zeros. So, for example, the graph of the polynomial function f of x is shown in the figure on the right. It is known that x equal to I square root of 3 is a 0 of f. Automatically, your brain should see, if this is a 0, what is also a 0? Negative I root 3 is also a 0. We got to know that. The question then asks, if f is degree n, what is the least possible value of n? Basically, what could the degree be? If we look at the graph, how many zeros are visible on the graph? I see why you said that, and you're not wrong. I can see that there are 2 places where the graph crosses or touches the x-axis, but actually, what is happening at negative 1? It's bouncing, it's tangent, which means how many is there? 2, maybe 4, maybe 6, some even number. But we know that because this bounces or is tangent and this one crosses through, that this is going to be an even power and this one is going to be odd. Since the question asks me for the least number, we are going to say 2 and we are going to say 1. Those are the least even and odd numbers. So we would think, okay, the zeros of the function are x equal to plus or minus I root 3. We got that from the question. They are also x equal to negative 1 with the multiplicity of probably 2. And 3 with the multiplicity of probably 1, especially if we're trying to find the least. It could be 4, it could be 6, it could be 3, it could be 5. But the least number is 2 and 1. Therefore, what is the least possible value of the degree of this function? Not 3. 5. Why 5? Yes, I see 3 real zeros, but we were also told that this is a 0, which means this is also a 0, so I got to add 2 more for those imaginaries. So we say the least possible value of n is 5 due to the fundamental, yes, we're going to write all of that out, fundamental theorem you can shorten, of algebra. That is why. A lot of times in this class, if you haven't noticed yet, we're going to be giving sentence explanations for why things happen. So memorizing the names of some of these theorems or the formulas we're using, probably super beneficial. Does that make sense? So don't let the graphs trick you. You can see the real ones. You cannot see the imaginary ones. You have to read the question and make sure they didn't tell you there was an imaginary one. Because then you have to add that one in and its conjugate in. Okay, here's where the highlighting section of our notes takes place. Again, I recommend having at least 3 colors, probably exactly 3 colors. When we are solving polynomial inequalities, especially with a graph, when we write f of x, remember we are talking about the output or y value on the graph. That's what f of x means. It's the name of the function, yes, but it's talking about the outputs or the y's. When I ask you the question, f of x greater than 0, I'm going to use green for this one. You'll see why in a minute. The f of x greater than 0 means that I'm asking where the graph of f of x is above the x-axis. If I ask you f of x less than 0, I'm using red for that one all day, it means where the graph is below the x-axis. So when we're looking at a graph, it's a very visual answer. I've answered all the questions here for you. I want us to figure out why these are the correct answers and how that changes depending on what I ask. So before we actually look at the answers here, on your graph, I want you to do the following. Anywhere the graph is above the x-axis, I want you to highlight the actual curve in whatever color you picked as above. So for me, I would do like this. That's the section of the polynomial here that is above the x-axis. And then I want you to go back with your less than 0 color, and I want you to highlight the sections that is less than the x-axis or below the x-axis. Then with your third color, if possible, because I know sometimes the colors bleed together, I want you to go back and I want you to highlight exactly where the graph is equal to 0. When we describe the intervals for each of these questions on your paper, we are describing the x values where these certain colors appear. So in the first question, and I know you're still highlighting, but I'm going to keep talking. It says, where does f of x equal 0? Well, it equals 0 exactly where I put those blue dots. At -3, at -1, and at 3. Do we understand that part? Okay. The next question says, where is f of x greater than 0? That means I'm trying to answer exactly where all the green part is. Look at what's typed there for the answer. It says, start at -3 with the parentheses, which means it's not included. End at -1 with the parentheses, which means it's not included. And, or, I always say and, it's or from where 3 starts, not including 3, all the way to infinity. Based on our graph, that is exactly the x values that are green. From -3 to -1, not including those blue dots, because that's where it's equal. And then starting at 3 and going to infinity. Do we understand? Okay, thank you for nodding. The next one is an interesting one. It says greater than, but also equal to. What has changed in my answer from part B to C, the way I wrote my answer? The brackets. What do those brackets mean? That is equal. It's closed dot. So because it says that it's greater than and equal, I can now change those endpoints to brackets to say also at -3, also at -1, also at 3. Not just immediately after them. Same thing for where it's less than, it's the same idea. If I ask you where it is less than 0, I'm just asking where is it red. It's red from -infinity to -3, but not including -3, because at that point it's equal to 0. And then from -1 to +3. And vice versa on the last one. That one's asking less than and equal. So again, like you identified for the other part, those parentheses change to brackets because it is actually equal to 0 at these 3 points. Just as a review, is there ever going to be a bracket around one of the infinities? No, because we can't actually touch infinity. It's a concept and a number, which is trippy when you think about it for too long. Does graphing it make sense? And I know that we did this in Algebra 2 and that for the most part it's pretty clear. What's not clear, because I already taught it to you once this year and I know we all panicked, is what's on the next page. Solving nonlinear polynomials inequalities by hand. So not by graphing. Now again, I've already done an entire problem here for you, so you have a nice one to look at when you're trying yours. But I am going to ask you a few questions about it. So let's walk through what I've done on number 4. Step 1 is to set it equal to 0 and solve it. That's what I did using the zero product property to get the critical numbers that go on the number line. We create a sign chart, which is all the signs, that's the sign chart part. And then test values in each interval to see if the values in the interval are positive or negative. Interpret the sign chart to answer the given inequality from the problem. We're going to write our answers in interval notation and make sure we think about endpoints. I put these little faces on there because I think some of us are too polite to say we don't remember this stuff. So if you're like, I've never known why it's parentheses versus bracket, it's the little face. if you have an open circle or one of these two symbols or an infinity, you're going to use a parenthesis. If you have one of these symbols that's all straight and stuff, you use the straight one. It's a closed dot. Hopefully that helps. Okay, so if we look at this example, what is the actual question here? What am I asking you to find? It's a great question, Ms. Cooley. You're right. I am asking you to find where this graph is greater than or equal to 0. So I'm looking for all the places where the graph is positive or where the outputs are positive. So I solved for this using the zero product property. I got the critical numbers. I put them on my number line. What did I do in this section here? What is this saying? Maybe specifically this one. What did I do with x equal negative 10 and why did I pick negative 10? Where's negative 10 on that number line? Yeah, isn't negative 10 like way over here? So I'm testing that first interval to see if the outputs are above or below the x-axis. I'm essentially, in my brain, plugging in numbers into this equation. Negative 10 minus 3 is a negative number. Negative 10 plus 1 is a negative number. Negative 10 plus 4 is a negative number. But a negative times a negative times a negative is also negative. So that means this section right here is going to be negative. I wasn't able to type this on there because I couldn't quite figure out the formatting. Go ahead and put a negative on that little section. The second section, I plugged in negative 3 because negative 3 is between negative 4 and negative 1. Yeah, you could have used negative 2. You can use negative 2.5. I don't think you want to, but you can. When you do that, you get negative, negative, positive, which means this section is positive. We continue by plugging in 0 and then plugging in 10. We get the following. Now again, what was the actual question? Where it's greater than or equal to 0, which means I want to know where it's positive. So if you notice, now that I've colored in that number line, which I recommend doing to show that that's the positive part or the above the x-axis part, those numbers and that interval now correlate to what I used as the solution. From negative 4 to negative 1, inclusive because it can be equal to, and from 3 to infinity. So we've already done all of the work. My question for you on this, before I let you try a whole one on your own, how would the interval change if the inequality actually was this? We've already done all the work. What would be the answer if I asked less than 0 instead of greater than or equal to? The opposite, yeah. So what number does it start at? What interval would it start at? Negative infinity, and it would go all the way to what? Negative 4. Do I use a bracket or a parentheses? Parentheses, because it doesn't have the or equal to underneath it. And then where else would I include an interval? Negative 1 to 3. So the work part of this, yes, is difficult, but once you have it, you just go back and check what the actual question is. Because the work's all the same, then you check the last part for the actual question. Can you guys try one? All right, you've got example 5. I've got a whole example right there for you. I want to see if you can get both the regular example question and then how it would change. I'll give you some time because I know this one is going to take us a minute. Let's talk through that sign chart then. So I think everybody pretty much got here if you didn't get further. When I'm doing the sign chart, I'm going to pick numbers in each of the intervals. I'm going to pick easy numbers. You can pick like negative 5, negative 10 because those are less than negative 2. This time I'm going to pick negative 10 just because it's significantly less than negative 2 to really emphasize my point. If you take negative 10 and you add 2, are you still going to have a negative number? I'm talking about this factor right here. Negative 10 plus 2 would still be negative, right? What happens when you square a negative number? It's positive. I'm going to leave that there for a second. If you take negative 10 and you subtract 5, that's still negative, which really means this is like a positive times a negative, which means that section is negative. Ooh, did we remember about the square? You know, those, oh, math teacher does the easy one. We do the hard one. I know. I'm sorry. Okay, for the next section, what number is really easy to use to plug in? 0. Oh, we love plugging in 0. It's so much easier. 0 plus 2 is a positive number. 0 minus 5 is a negative number. Positive squared is still positive, which means that section is negative. This is why we do a sign chart. You can't automatically think they're going to go back and forth every time. For the next one, I'm going to pick 10 just because that's significantly bigger than 5. 10 plus 2 is a positive number. 10 minus 5 is a positive number. Positive squared is still positive, which means that section would be positive. Okay, cool. What was the actual question here? Less than 0, which means which two sections are we going to include in my answer? We want to answer from negative infinity to negative 2. Take a little pit stop at negative 2 and pick your pencil up. Then go from negative 2 to 5. You have to show me there's a break in the middle at negative 2. Because it is equal to 0 at negative 2. And we just want where it's less than. It's tangent to the graph there. It bounces off the graph there. Questions, comments, concerns about that? Here's a little bonus question. What happens if I change the inequality and it's actually this question? Less than or equal to? How does that change your answer? Ooh, okay, love that you said that. Thank you for falling for my trick. So you said just add brackets, so you're saying something like this, right? I see why you say that, but that's not exactly right. What's happening now that I've changed brackets? Does it touch negative 2? If it touches negative 2 here and touches negative 2 here, we've just done a whole bunch of extra describing. Here's how I would want you to actually answer this question. If it says less than or equal, we're actually going to change it to from negative infinity to 5. Because it touches 2. It goes through it right there. We don't have to stop and pause if it's part of the inequality that I want. I get why you said that. Thank you for falling for my trick because that's exactly what I wanted. Okay, so if you would have a double bracket around the same number in different intervals, you can just smush the intervals together, is basically the point. Does that make sense? Okay, two more topics that again, oh yeah, what's up?
The first way that you wrote it wrong.
I don't actually know if AP would count it wrong, and it would be subjective upon a college professor. I would say it's wrong because he's done too much, but a professor or like a textbook might accept it because it's describing the intervals just in a really complicated way. I'll look it up for AP. I'm not sure if AP counts it right or wrong. I'm assuming no because they make a big deal about nothing extra on it. Thank you for asking that. This section is about determining the degree of a polynomial given a table of values. Now, I'm sure you're stressed out because every time I've given you a table of values, you've had to do average rate of change. And I made a big deal about not just doing that cute little, like, this number. You know what I'm talking about? That was because the tables that I gave you were not what are called equal length intervals for the x's. But if the tables you get are equal length intervals on the x's, meaning the x's are changing at a consistent rate, plus 2, plus 2, plus 2, plus 2, you can do the cute little thing on the side of your table. That is not what I gave you when we were studying average rate of change. This is why this is different. Here, plus 3, plus 3, plus 3, plus 3. We can do the cute little, like, on the side of it. So that's what we're going to do to talk about differences. The important thing is, I guess I should read that. We can determine the degree of a polynomial talking about the successive differences in the output values. The number of successive differences needed for the differences to be constant is equal to the degree n of the polynomial. So we're going to keep doing the little change in the y's and the changes in the changes and the changes in the changes of the changes until we get a consistent number. Meaning, we do the following. How much does it take to go from negative 2 to negative 3? Minus 1. How about from negative 3 to negative 1? Okay, keep going. What's this one? Plus 5. What about this one? Okay, cool. Are those all the same number? No. So we do it again. How do you go from negative 1 to positive 2? I'm second guessing myself now that you said 4. Is it 3? Wow, I really had a whole second where I was like, is it? What about from 2 to 5? And 5 to 8? Now, are those the same number? Great. So how many times did I have to do those differences for it to be constant? 2. This is a degree 2 polynomial because the second differences are constant. If those weren't constant, we would keep going for the 3rd degree, 4th degree, 5th degree, on and on. Does that make sense? I think y'all have done this before, yeah? Again, we're able to do this unlike the average rate of change because these are all the same difference. They're all +2 on the x's. Yes? It would be degree 1. It would be called linear. Because the first difference is it has a slope. So it's okay if it's 1. It would be degree 1.
So that's degree 2?
That's degree 2. That would be a quadratic, yeah.
No, but I mean, like, if you keep on going to where it's only
I wouldn't do that to you. You'd have to be able to tell the differences. I'd have to give you more numbers on the table. Yeah, I see what your question was. Okay, if we do B, I think y'all are already ahead of me. How does this change? +2, how does this change? Oh, definitely, obviously not the same. How about this one? Yikes, how about this one? Okay, great. Those are obviously not the same numbers, so we do it again. From 2 to 10 is +8. From 10 to 17 is +7. Plus from 17 to 23, 6. Those are obviously not the same. We do it again. What about this one? And then, those are the same number. Which means what degree is this polynomial? Because the third differences are constant. Bonus question here. What kind of polynomial would that be called? Cubic. It is, trinomial means 3 terms. Not the power 3, that's a cubic function. Okay, our last random topic in polynomials for today, again, I told you it would be a huge vocabulary day, is about even and odd functions. Now, I think you've gone over this before, but probably not in the way I'm going to have you go over it, because most likely you looked at a function on a graph for even and odd, or at least we're only comfortable looking at a graph for even and odd, but we're going to do it analytically as well. An even function does not necessarily mean that the degree is even. An even function means that the function is symmetric about the y-axis. So take your highlighter right now, and I want you to highlight the y-axis for this graph. If we were to fold your piece of paper like a pancake along that highlighted line, the left side and right side of the graph would lay right on top of each other. It's symmetric about the y-axis. Amazing, great. But if I don't give you a graph, or if you're not confident, what I also need you to know about even functions is that if we plugged in a negative x value to the function and simplified, we would get out the original function. That's an even function. So plug in a negative, get out the original. An odd function is symmetric about the origin. So again, you probably only saw this by a graph, and there's many ways to talk about what is happening. I like to do the following. It's a double reflection, but I find that hard to visualize on my paper. In my head, you take a pin and you stick it into the graph at the origin, and you rotate the graph around itself. And this is hard to do because the screen doesn't follow my iPad, but I'm going to zoom in on my iPad right here and just flip it physically with my hand. But if I put a pin right here and I spun my iPad, doesn't that look the same? That's odd. If you can put a pin in the origin and rotate it over and it looks the same, that's odd. It is a double reflection. It's a reflection over the x and then the y. That's another way to think about it. I like to rotate things, so that's how I've always remembered. For analytically, an odd function means that when we plug in a negative x, we get out the exact opposite of the function. Odd opposite. Odd opposite. Odd opposite. So when I ask you to determine if polynomials are even, odd, or neither, you do not look at the degree because they're misleading sometimes. When it's not graphed for you, we're going to plug in a negative x and evaluate. Meaning, if I was doing part A, I already started it for you so you can understand what's happening here. I'm going to determine if it's even, odd, or neither. I want to plug in negative x. That's what I'm telling you to do right here. So everywhere there was an x a second ago, what did I put in its place? Negative x. If we evaluate, so we're going to do some math. What is a negative number to the 4th power? Which means it would be negative times negative times negative times negative. Positive, which means this little section is still 2x to the 4th power. Because a negative times a negative times a negative times a negative is positive. Okay? What about the second part? What is negative x squared? Negative times negative is positive, so this is positive x squared. I didn't plug anything on 5. Then we compare. What you evaluated after plugging in a negative x, is it the same or opposite from where we started? If it's the same, what is that called? even. This is an even function because f of negative x is exactly equal to, oh, this is h. Let me use the right letter. H of negative x is equal to h of x. We got the exact same thing when we plugged in a negative x and evaluated and simplified. Misspelled the word because. That's embarrassing. Okay. Can we do that again on B and C? And by we, I mean you. I've started them for you. You're going to simplify the things I've told you and then compare it to the original. If it's the exact same, it's even. If it's the exact opposite, it's odd. And if it's a weird combination, it's neither. Okay, I think some of you fell for my trick again. Aha, thank you. So if we filled this one out for B, I've already told us we're plugging in negative x and done that for us. If we do negative time negative time negative, what is that? Negative. So this is negative x cubed. So it's an, ooh, that's a weird looking 3. Let me try that again. And then 3 times negative x is negative 3x, and then negative 1 just drops down. When I compare this to this, is it the exact same? Is it the exact opposite? No. It is not the exact opposite because the first two, the sign changed, but did the last term, the negative 1, did the sign change? No, so this is neither. Because it's not the exact opposite and it's not the exact same. So this is neither even or odd. Most functions are not even and odd. Most functions are not even or odd. They have to be very specific to have the property of even or odd. Okay, when we do the third one, again, we would be plugging in negative x. Negative time negative time negative time negative time negative is negative. So this is negative x to the 5th. And then negative time negative is positive. When we compare these two, are they the exact same? Are they the exact opposite? Yes, since this one is opposite, this is called odd. And again, it's odd because when we plugged j of negative x in, we got the exact opposite of the original function. That's the formal analytical definition of even and odd functions. But it is also easy to answer these questions graphically because it's a visual concept. So if you had D and E, it's very easy to see if it's even or odd. For D, can you fold it along the y-axis and it land right on top of itself? No. Can you put a pin in the origin and rotate it around itself? Yes. So this is odd. For part E, can you fold it along the y-axis? Not this one. If this quadratic was centered on the y-axis, it could be. But this is off-centered, which means it doesn't fold. Does it rotate around the origin? No, so what would you call this one? Neither. Which is why I wanted to make a big deal about don't look at the degree. This is some sort of x squared polynomial. That's an even degree, but it is not an even function because it is off-centered.